Hi, everybody. This is Elizabeth Hammond, and I am hosting this talk and introducing it. And I am really happy to be here. I have to admit, it's a bit peculiar just to talk to my computer and think that you're listening. So I think it'll be the same for Brian. But anyway, I'm glad you're here. I am the principal investigator on the Sustainable Adaptive Gradients in the Coastal Environment National Science Foundation project. And this is part of our webinar series. It's the third and concluding talk for this fall. We're working on our schedule for the spring, but our next speaker will be the coastal engineer and geoscientist, Robert Weiss, who's an associate professor at Virginia Tech. I anticipate that'll be sort of late January, but we'll send the final date for that a bit later. And just as a reminder, we have a pretty good website, great I even think, but at www.resilient-infrastructure.org. And that has a link to the YouTube channel, on which all of our webinars get posted, so you can review previous webinars as well. Today, it's my real pleasure to introduce Dr. Brian McAdoo, professor and college rector for Yale-NUS at Vassar Yale-NUS in Singapore. Brian was previously at Vassar College, where he served as the Althea Ward Clark Professor of Environmental Science. He was trained in geology from Duke University, as well as the University of Otago, New Zealand, where he was a Fulbright scholar. Did his PhD in Earth Sciences at UCLA Santa Cruz. And a fun note is that for that, he completed 8 dives to the bottom of the ocean in the deep sea research vessel Alvin, looking at submarine landscape evolution. So maybe he can regale us with some tales at the bottom of the sea. This research eventually led to an interest in earthquakes and tsunamis. And following the 2004 Indian Ocean disaster, he participated and led post-disaster reconnaissance teams in Sri Lanka, the Maldives, Banda Aceh, the U.S. Gulf of Mexico, Solomon Islands, Samoa, Java, Japan, and Haiti. So he has seen in a very direct way what happens after disaster and what resilience really means. This led to a significant interest in identifying how researchers can communicate more effectively across academic disciplines between the academy and the public sector. Professor McAdoo is currently working with UNESCO, the Partnership for Environment and Disaster Risk Reduction, and the International Union for the Conservation of Nature to design transdisciplinary post-disaster surveys where critical information can be effectively delivered to reduce disaster risk. And on a personal note, one of the things I'm really happy about here is, first, Brian was one of the He was one of the idea originators behind the whole SAGE grant. So we started talking about this a few years before the whole project started. And then he went off to Singapore and got this rather prestigious position and doesn't have, so he's doing that in addition. And also, I'm always tickled to talk with him because he's one of the people who really combines a deep knowledge of physical science and a commitment to social equity and justice. And it's just a really powerful combination. So I couldn't be more pleased to introduce Professor McAdoo. In particular, I want to thank him because I think it's midnight in Singapore. And I can't quite imagine, it's strange enough to talk to your computer, at 11 o'clock on a Friday morning, but it must be even stranger at midnight. So with that, I will turn it over to Brian.
Thanks very much for that kind and a little embarrassing introduction, Elizabeth. Appreciate your words. And it is indeed midnight here in Singapore, but I think I only had one beer with my burrito at dinner, so hopefully I won't fall asleep halfway through talking. Hopefully you won't fall asleep. Elizabeth mentioned, I'm at the Yale-NUS College. It's a joint venture between Yale University in New York and the National University of Singapore. And it's really the first liberal arts college of its style here in Asia. And it's really a fantastic place to be doing liberal arts and truly interdisciplinary education for undergraduates. We're still a fully undergraduate institution here. But it allows us to do some things that I find quite fun and exciting to do, especially in this part of the world where there's a lot of different factors coming into play. We have a lot of changes in the natural environment going on with increased pressures on land use and the like, but also incredible growth in the economies and populations of this area. Climate change can have some interesting effects in the tropics down here, and all kinds of things are converging right here to make it a very interesting place to do some work. What I want to talk about today is this convergence of different disciplines. Is liberal arts education can bring different fields together. Some people in academia consider, a combination of biology and chemistry. Biochemistry is kind of a radically interdisciplinary pursuit. But what I want to talk about today is something a little bit more. We actually look at how do we bring together both historical perspectives, cultural perspectives, along with the geophysical, economic, engineering perspectives on disasters. So it really is what I consider a truly radical approach to studying disasters. And the key, as Elizabeth mentioned also, is understanding the different roles that people play. And I think the better we understand our roles in this field, which I think a lot of us are trying to do, is actually reduce the losses from disasters. If we understand our roles better, then I really believe we can be more effective in doing our work. So with that, I want to start off with perhaps some crazy talk. I was at a UN conference, I believe it was in 2005, and the diplomat in probably a $5,000 suit in Geneva comes up to me and says, there's no such thing as a natural disaster. And I probably sprained my eyes rolling them because I just returned from Aceh province and said, this is crazy talk. But it's one of those things that kind of got you thinking about it, and you realize that people who are in this work, have dedicated their lives to it, and there really aren't that many truly crazy folks out there, and there's usually some truth in these different things. So in saying there's no such thing as a natural disaster, I think the focus is on natural. And really, prior to 2004 Indian Ocean tsunami, there really was a focus almost entirely on reducing the losses from natural hazards or natural disasters by focusing entirely on the hazard. We spent a lot of time looking at sources for earthquakes and how to calculate better models for wind speed in typhoons and climate models with heat waves and drought events. But since then, we've also been paying a little bit more attention to the role of social vulnerability, resilience, and all these words we've been talking about in the SAGE project. Also, as Elizabeth mentioned, I kind of got into this work as a liberal arts professor in Aceh province. This is a panorama of Glebrook village in Aceh. There's about 4,000 people passed away in this village during the 2004 tsunami, about 5,000 people. So you can see the landscape here is completely flattened by the tsunami. However, arguing that this is not a natural disaster is a bit questionable. Similarly, we did some work after the Tohoku earthquake and tsunami in 2011. This was a magnitude 9 earthquake. The average runoff was not extraordinary, between 5 and 10 meters, most places up to 15 meters in some places. On hillsides it ran up to 40 or 45 meters, which is truly a massive tsunami, killed upwards of 16,000 people. It was also the most costly of natural disasters so far, and over $300 billion US in losses. Another event that happened in this part of the world was the typhoon Yolanda or Haiyan, happened in 2013. This is one we did not respond to. We've been a little bit busy building up this new institution here in Singapore, but it's one of the largest and most powerful typhoons recorded as of yet, perhaps a harbinger of things to come with climate change. 315 kilometer per hour sustained wind speeds is really remarkable. Now contrast those three events with a magnitude 8.4 earthquake that generated a 15-meter high tsunami in the Kurile Islands in 2006. It's one of those things like if a tree falls in the forest, does anybody hear it? It's an uninhabited island. It ran up. My colleagues from the University of Washington had been there the year before, and they came back the following year, and said, oh, that log wasn't there. And they noticed some evidence of erosion, some sediment about deposition in different places, and said, oh, looks like there's a tsunami here. And they ended up mapping it out and found out there was a significant tsunami. But because there was nobody in the way, because there was no vulnerable elements in this particular region, it did not turn into a disaster. So starting off with that, there's no such thing as a natural disaster. Perhaps, you can't always blame the, you can't always blame the geophysical hazard, no matter how much we understand about the geophysical hazard itself. I would argue that it's also critical for us to understand the vulnerabilities, resiliences, capacities of the entities in the way of these different hazards. Kind of play on words, the title of this talk was not the earthquake's fault. I think we'll see what I mean. You can't really focus entirely on the geophysics of these events. This is an interesting graph that was originally published by Roger Billam a few years back, and I added another image there, another data point from the Japan tsunami. But you can see on this graph, you would predict that there should be somewhat of a linear scale, even on this log graph, where you have increasing magnitude of an earthquake should result in increasing deaths. However, you can see an event like Sumatra is about right. It's a really big tsunami, really big earthquake, powerful earthquake, and it actually killed a lot of people. Japan was almost an equally large earthquake, but killed an order of magnitude less people. And the Haiti earthquake was not such a big earthquake. And speaking a little bit to the vulnerability of that society, we don't really know how many people died in that earthquake, so we didn't have enough records to know how many people were there before the earthquake. So it's really telling to the vulnerability of that particular situation. What we've been working on since the 2004 earthquake is kind of a framework for understanding how these disasters come to be, and how, as a geoscientist working in this really complex world, I can define my role as a geoscientist and how I interact with other people in the field. Even as a geoscientist, we have interdisciplinary geosciences where, as a tsunami scientist, my role is to understand, in some ways, something about seismic activity, and a little bit about earthquakes, and something about mass movements, in this case, water. So perhaps a little bit of fluid dynamics, a little bit of seismology, to understand enough to ask questions and have conversations with the people who are experts in these fields. If we take that and make it a little bit more complex and consider the resilience or vulnerability of different systems in here, this could be things that break or things that could break. Ecology, living systems, human systems, and ecosystems really here, things that can be harmed by exposure to natural hazards. If I understand that, in the case of a tsunami, say a community that's living in Aceh, I have to understand a little bit about seismology, a little bit about mass movements, but also something about the sociology, the economics, the anthropology, and even the ecosystems that these poor communities rely on in this coastal zone. So I have to know a little bit about mangroves, a little bit about coral reefs, about fisheries, a little bit about agriculture, rice, vegetables, that sort of thing. And like I mentioned before, we are also interested in solutions. We can sit back and point out problems. We're quite good at doing that, but actually saying what's that next step at pointing out how we're going to do something about it is really the challenge. That's why it's been my pleasure to work with the SAGE group, because they have this group of people called engineers. And engineers are really tasked with solving some of these problems that scientists are so good at pointing out. Similarly, I also argue that policymakers are kind of engineers. It's the job of policymakers to sort of engineer behaviors. So if you have people who are charged with setting up policies for evacuation of a coastal zone during a tsunami, or building codes that the engineers have to follow, that falls in the lap of policymakers. So really to get a good grasp of the overall situation we're looking at in these complex, especially coastal hazards, we have to know a little bit about a lot of things. It's an argument for a breadth over depth approach that liberal arts colleges, especially places like Yale and US, really celebrate. I hope I can have semi-intelligible conversations with the colleagues in the SAGE project who are engineers, policymakers, ecologists, also seismologists and sedimentologists in the group. And by respecting them and their jobs and their spheres of expertise, I think we can really move forward in these conversations. We'll get going. What we're talking about here is this idea of risk, disaster risk reduction. And I wanted to put out a definition here quickly so we're all on the same page. Consider risk the probability of a negative impact on a community, injury, damage, or loss that results from exposure to hazards. That's easy enough, but you could risk winning the lottery, but I don't think anybody would really be concerned about that. It's very simple formulations that have been worked on over the past 10 or 15 years, where you consider risk in the context of natural hazards or natural disasters as being an intersection of a hazard with a vulnerability. So in this case, we have an image of the tsunami that's hitting Thailand, Koh Phi Phi in Thailand, and some people that may be living in that area. It turns out these people happen to be from Aceh province, but it's a different thing. But you can see how they actually survived the tsunami in 2004 because they had certain policies in their family in place. But these are still people who can get hurt. Well, I proposed this to one of my students, and she was a social scientist, and I have this hypothesis that social scientists have a way of taking something that could be very simple, like why is my teenager acting like a jerk, and making it very complicated by saying, oh, there's all these different reasons. It's very complex and exploding all these reasons, where it's the job of a geophysicist to take a very complex system, which is the Earth, and make it very simple, break it down to its most simple components. So really, when it comes to understanding the geophysical hazard, the role of geologists in that is saying how frequent and how large a magnitude of these events going to happen. How big, how often are they going to happen? That's really the core of what our work is. We can talk about the physics of how it happens, but that's in some ways icing on the cake. But understanding how big and how often these things happen is really important. My student, though, said, well, McAdoo, you can't always go in talking to people about vulnerability. We can change our language to thinking about what can people do to actually help themselves, rather than saying if you're coming to an event, you're in really big trouble. We actually have strengths. There are certain ways we can bounce back from these. So instead of just considering risk as the intersection of hazard and vulnerability, we also have resiliences, which are kind of counter to vulnerability, and mitigations, things that engineers and policymakers can take on that will reduce the risk, ultimately reduce the risk of disaster in a given area. I want to go through a couple of examples in a little bit more depth to show how these systems come together and can be really quite complex. In 2010, we're all aware of the relatively mild magnitude 7.0 earthquake that hit Haiti and killed anywhere between 86,000 to 316,000 people. Really not sure, but best estimates put it about 150,000 people that died during this one event, and about $8 billion in losses in a country where the entire GDP at the time was about $11 billion. A book came out a few years back called The Black Swan, and they talked about how these outlier events are part of chaotic systems and the like. And the common theme to that is that human behavior can't really be predicted. Therefore, really, the punchline I would imagine from this book is that humans are really the black swans. They would argue sometimes in an event like the Japan earthquake, you have a bunch of magnitude 8.6, 8.5, 8.4 earthquakes, and then boom, you have a 9.0 or 9.1, that's a black swan event. I don't think so. Those events are governed by physics, not by erratic human behavior. But I think you'll see that I think mostly the human behavior is responsible for the magnitude of some of these extraordinary disasters. We look at this part of the human system then, and considering human behavior and how human behavior can affect ecosystems and also the systems that humans live in by looking at Haiti as an example. Looking also in this case, focusing on the economics and the history of the area and how that can actually really affect the geology. Sometimes you think the geology might affect that, and it certainly is a feedback. Excuse me. If you look at Haiti prior to the earthquake, there was extreme urbanization happening in Port-au-Prince. People were moving, seeking economic activity in the city for very good reasons. The countryside is some of the poorest in the Western Hemisphere. As we've always heard, turns out that Haiti has not always been the poorest in the Western Hemisphere. And in fact, prior to the Haitian Revolution, starting about 1791, the island of Haiti itself is responsible for 1/3 of France's GDP. So it's a very natural resources rich island. There's no reason that it should have been indebted in poverty for the last 3 centuries, but we can talk about reasons why that was the case. But people in the countryside were decimated by poverty and hunger and famine and poor education, poor sanitation. So they sought economic opportunity in the city, and it resulted in extreme urbanism like this. So when the earthquake happened, the combination of poor building structures, they had just enough money to buy concrete and the like. They built houses designed to withstand hurricanes that hit the island quite frequently, but they were poorly enough constructed they could not withstand a magnitude 7 earthquake. So when the earthquake hit, a lot of these buildings just crumbled like stick houses. But of course, concrete weighs a lot more than sticks. So the vast majority of deaths here were caused by buildings falling on people. This is a Google Earth image of Port-au-Prince. I just want to point out the location of the Enriquillo Fault went right through the area just to the south of Port-au-Prince, but really right next to Port-au-Prince. The section that ripped was actually not going right through Port-au-Prince. We think it could, the next section could rupture and could go straight through the urban metropolis of Port-au-Prince, which could be even worse than the 2010 event. The title of the talk, again, I'll remind you, is not the earthquake's fault. I'm going to go back in history a little bit to think about how events like the Haitian Revolution that took place in 1791 to 1804, one of the first successful slave rebellions in the world, resulted in the formation of the Free Republic of Haiti, even though it wasn't quite free at this point, because the revolution was successful and because they massacred up to 15,000 of the remaining white settlers on the island. France fined Haiti essentially an extraordinary amount of money. I can't remember the exact amount of money right now, which to this day Haiti is still working on paying back. So they started their freedom in debt, and they were never quite able to come out of that. And because of that, they were never able to really, partially because of that, they were never able to really build up the economy. Another factor that came into it, after being in a slave plantation economy for such a long time, where they had large landholders with large numbers of slaves on these different properties, producing mostly sugar and some coffee, I think. After the revolution, they decided, you know what, we're not going back to that system. We want every man to have their own land and take care of their own family, which resulted in a classic tragedy of the commons situation. Further on down the road, also, Haiti suffered from a combination of classic dictators. This is an image of Francois and Jean-Claude Duvalier, just some real nasty characters who robbed Haiti of what little wealth it had, leaving the country in extreme poverty, which I'll show you in a minute, resulted in environmental degradation that made them more vulnerable to the earthquake when it happened in 2004. Going back also, I want to show this image of Port-au-Prince. The capital of Haiti is called Port-au-Prince for a good reason. I mentioned before, Haiti has extraordinary natural resources. The port, the natural harbor where Port-au-Prince is based, is one of them. You can imagine most of the hurricanes that would come in from the east towards the west would hit the western part of the island, leaving a beautiful, almost perfect safe harbor here in Port-au-Prince. But of course, this harbor is created by the network of faults that crisscross the island. The Enriquillo Fault there in red is the one that's responsible for the 2010 earthquake and many earthquakes that had destroyed Port-au-Prince 2 or 3 times prior to the 2010 event. There's another city that has a very similar geography, San Francisco Bay Area. This is at the same scale. You can see the San Andreas Fault there to the left of the image on the left image, and the Hayward-Talavera systems crisscrossing the Bay Area. They actually are responsible for generating San Francisco Bay, another beautiful safe harbor that has caused San Francisco to have a lot of its wealth. And both cities were hit by earthquakes of relatively similar magnitude, but the outcome of these earthquakes really argues for vulnerability being mainly responsible for the magnitude of the disaster. The 1989 Loma Prieta earthquake was a magnitude 7.1. There were about 7.4 million people in the Bay Area that were exposed to strong shaking. Population density in San Francisco was about 6,700 people per square kilometer. The total deaths from 1989 was 63. The gross domestic product, if you take that for the whole Bay Area, is about $300 billion. And in San Francisco alone, there are 42 fire stations. Let's compare that to Haiti, which got hit by the magnitude 7.0 earthquake. There's 10 million people in all of Haiti. The population density is where things start getting different. And you can see the population density in Port-au-Prince is amongst the highest in the world at 28,000 people per square kilometer. The earthquake resulted in, I mentioned before, 130,000, 230,000, 300,000 deaths. We don't really know because their records were so poor, the government was barely functioning. When the earthquake hit, there was GDP of all the country was $11 billion, which I find remarkably high, but that's what it was recorded as by the World Bank. And in all of Haiti, there are 2 fire stations whether they're active or not is another question, giving you a proxy for how not resilient this country was when this event hit. So this is one example of how humans can affect the environment, how human poverty can be affected by earthquakes and the interaction of this. But I also want to show an example of how humans can affect the geology and the actual long-term vulnerability and actual hazard of an area. We'll get to that in a minute also. As I mentioned before, Haiti was racked with extreme poverty when the earthquake hit. Between the Duvaliers and the French Revolution, the reparations put on France from after the Revolution, it was extremely poor, and the countryside was faced by, people in the countryside were faced with extreme poverty. This is an image that's very familiar to a lot of people, the border between Haiti on the left in the deforested area and the Dominican Republic to the right, which has a lot more forest area. It was actually a legacy of these two different dictators who took very different approaches to how to govern their countries. The Duvaliers were classic kleptocracy, where they took a lot of money and hid it offshore. Rafael Trujillo, excuse me, the Dominican Republic, actually massacred a group of Haitians that had crossed over the border to deforest to get fuel for food. I can't remember, it was upwards of, I think, 5,000 to 10,000 people were killed in one incident. And he threatened to dispose of people who were caught deforesting in the Dominican Republic. And to get fuel, he was able to allow his brother, who had a fuel company, to supply all the fuel for the hinterlands, thus feeding his own pockets in an environmentally thoughtful way. The result of this, the legacy of this poverty was brought home to me when we were visiting Haiti in 2010. This picture actually really broke my heart. This is an image, I can't remember exactly what the French word for the Creole word for this process is, but the people who lived in this rural village were farmers, and they needed fuel to cook their food. So they would chip away at this tree just enough so they wouldn't kill the tree, so they could still get these soil stabilization services from the tree, but get enough wood off of it for fuel so they could cook their food. This is what extreme poverty looks like in Haiti. And you can get an image of also how bare the landscape is and how susceptible it would be to erosion when the strong seasonal rains come, usually in August, September, October of the year. This is also an image from modern-day Haiti in 2010 on the trip we took there. You can see how the landscape has been cut into small land holdings that people try to farm. How they farm on these steep, almost completely denuded slopes is beyond me. You can see the evidence of erosion here that is really quite extreme. You can see the gullying and large amounts of boulders in the drainages here. Curiously, on the coastline, where these rivers come out and deposit sediment in the ocean, resulted in a small tsunami. And we heard about this on a CNN report. It actually killed upwards of 10 people in this village of Petit Paradis. Took us a little bit of homework to find out where it was, but the reporter said, oh yeah, this tree that was sitting out in the ocean was not there prior to the earthquake. So we did a little bit of homework, and we found this Google Earth image from before the earthquake. And I'm going to sketch in the coastline here. And then after the earthquake, you can see there's been quite a bit of land loss in this area. We believe that the combination of a little bit of uplift from the earthquake and also significant slumping from very, very loose, weak sediments, rapid sedimentation, overpressured sediments that are in the coastal zone, work together to generate the tsunami that killed the people in Petit Paradis. This type of landslide and coastal landslide was seen in several places near the epicentral area of this earthquake, and I think it's something that could use a little bit more work down the road. We did kind of an interesting study. A colleague, Matt Hornbach, went down to Haiti and actually crawled into the sunken, the destroyed shell of the Ministry of Geospatial Information or something, and was able to collect some old aerial photos that were in the crumbled building and traced out the coastline in this particular area at different times. This was published in Nature in 2010, a little bit later in a special issue. We went through and did a little bit more work on it. We just traced out changes in gross domestic product in Haiti as a proxy for poverty in the hills and see if that would relate to deforestation. And sure enough, if you look at the time of the Duvalier regime, there's extreme coastal progradation in this area, up to 8 meters per year. When it transitioned into more of a democratic type regime before I can't remember his name, Aristide came in, the rate slowed down, and as it started stabilizing even a little bit more, and we started actually seeing positive growth in the economy, the coastal progradation slowed down a little bit more, and then it results in the earthquake down the road. So we actually are able to trace a linkage between, or a very loose linkage, at least something we'd look at, between poverty in the hills, erosion, and coastal progradation that eventually resulted in a tsunami. One further example to show how extreme coastal progradation is in this area, I'm going to see if you can see my cursor here. This area in Léogâne, just outside of Port-au-Prince, is a very prominent delta. You can see the river that's feeding the delta going here, another delta over here, and another river that actually tracks along the Enriquillo Fault. You can see how pregnant this river is with sediment in this area. Keep your eye on these circled areas here. We're able to find a map in the archives in Sevilla, I believe, Biblioteca Nacional de España. These are the same areas in a map from 1780. Looking at those two areas that were very large deltas, you can actually see their bays. Now, I'm not arguing this map is any way scientific, but the French, when they're making this map, or the Spanish, when they're making this map, rather, were definitely looking for things like bays. You can see the rivers following those mountain ranges and emptying out into what were bays in 1780 and are present-day large progradational deltas. That's some places upwards of 80 kilometers worth of progradation in just under just over 200 years is pretty remarkable. As I mentioned before, the role of geoscientists is to sort out the frequency and the magnitude of these events. How often do they happen and how big are they when they happen? We did some work in Aceh province after the tsunami to try to figure out when was the last tsunami there. Catherine Monica published this in Nature a few years back and was the first one to show the penultimate event of the 2004 tsunami. She was able to find sediment in these ridge and swale topography areas, and the swales was actually a good catching place for sediment. And what she found was that though the 2004 event actually went quite a ways inland, the older events were the events got younger, events from the sedimentological events got younger as you went closer to the coastline, which makes sense depending on the magnitude of the events, what scouring happened in these events, and that sort of thing. So we're able to get an idea of how frequently tsunamis happen in this area. The last event in this particular area right here was in 1907. The last big event that happened up and down the coastline, we also have evidence was in Thailand and perhaps Sri Lanka, was in 1350, and prior to that was in about 850 AD. The next question we want to know is actually how big was this event when it happened, and that's something a little bit hard to do just from a sedimentary record. We proposed a model that would work on this, but we hit a wall with it, and I'll tell you exactly what happened in a minute. The way we tried to do this is we want to consider if we had a certain sediment distribution, sediment grain size distribution, what are the shear velocities it would take to actually move these sediment from the coastal zone or from the continental shelf or right at the swash zone of the beach inland. So we went through and calculated. This is work done by Andy Moore, who's now at Yale-NUS College. He was at Kent State University when this work was done. But to this, Andy went through and calculated critical shear stress first, to move a grain size of a grain of a certain size, maybe the biggest size in the sample we took, and then use the critical shear stress to calculate a critical shear velocity, and then use that critical shear velocity to get a depth average turbulent flow. So from this, we can start getting an idea of how fast the flow was moving to actually pick up some of these sediment and go on. So with that, you can get an idea of a range of flow velocities, but that doesn't tell you how big or what the flow depth was or how much water is actually flowing over land at a given point, because you can see the range can be quite wide. So we end up with two unknowns. If we know the flow velocity, we don't know the depth. If we know the depth, we're trying to find the depth. So what Andy decided to do is actually use a graphical solution to figure out what the flow velocity would be, or the depth would be, given a certain flow velocity. And to do that, he looked at a law of the wall type model where he looked at settling velocities and calculating the settling velocity versus Yeah, I can't remember exactly how. Andy went through into this, so I'm forgetting exactly how it was done a few years back. But you calculate setting velocity based on the length. It's kind of a ballistic model. You consider the length of how far inland it went, how long it took for that sediment to get in there. And based on that, you have an intersection of the graph at one place, and from that you can get an estimation of the flow depth at a given point, wherever that particular sediment sample is taken. The problem with this model goes back to that idea of the advection length. So we take a sample there at the X in that one particular swale. We don't know where the coastline was at that point. We believe that each one of these swales might be a beach ridge. Would have been an active beach ridge at some point, and perhaps the coast is progradating out. If that's the case, the advection length can vary somewhat significantly. And as we saw in Haiti, there's a lot of things that can actually affect the progradation of a beach. In this area, we're not sure what is governing the frequency of these ridges. A recent publication in Quaternary Science Reviews suggests that each one of these ridges is created by an earthquake and tsunami. So when the tsunami comes on land, the backwash actually takes a lot of sediment back offshore, and then slowly, as regular littoral processes kick in, it builds up another ridge. So we actually do see evidence of a ridge that was created, a big ridge that was created after the 2004 event, and we believe that the ridge that the village is on here would have been built up by a prior tsunami. Curiously, we went back to the records in the Netherlands and were able to find old maps. And again, while they're not actually scientific, a couple of things we can notice. In 1903, coastline has a little bit of a bend in it, and the river here is quite straight. There was an earthquake in 1907 where there was a small tsunami associated and perhaps some coastal uplift or subsidence. The coastline later was much more straight, and you can see the river here actually has some very significant meanders suggesting a lower gradient. So the coastline is a little bit steeper here, a little bit a lower gradient here. So there were some changes between these two. We're not exactly sure what those changes are, but something we should look into a little more and continue to study. Finally, I want to talk about solutions. We're very good at pointing out these problems, looking at these complexities of these systems, but what are we going to do about it is the question, and that's the work of people like Tom Sheehan and Don DeGroot, who we've been working with, to Lori Bays, who was on the previous grant we were on, to figure out, okay, how do we go about asking the questions to do this? What I'm going to argue, sorry, Don and Tom, if you're online here, is that engineering doesn't always work. We know there's failures, and we always hear about the failures. We never hear about it when it does actually work, but I had to pick on you guys a little bit on this one. Doing so, I was always curious, and I want to take an engineering class, so sometimes guys invite me to take one of your basic classes. I can learn something about this and realize the mistakes I'm making here, but I do actually admire engineers, and you know, we have definitions of engineering, and I've always tried to figure this out and wrap my brain around what it is. By the dictionary definitions, I figure that guys like me, earth scientists, are very good at pointing out problems, and engineers fix them. So I can sit back and say, yeah, there's a big fault there, and that fault ruptures every 300 years in a magnitude 8.6 event. Thank you very much. I wipe my hands and walk away. That doesn't do much good unless we can have that conversation with an engineer who can actually do something about it. So earth scientists point out problems and engineers fix them. I have to put another quote from my father-in-law up there. He says, engineering is science with accountability, which I think is a very clean definition. If I say there's a magnitude 8.6 earthquake that happens every 300 years, and it doesn't happen every 300 years, I say, oh, well, I guess it wasn't right. If an engineer makes a mistake, he or she will get sued. I want to point out some examples from the Tohoku earthquake. The title of this talk is not the earthquake's fault. I would argue in Haiti that the extreme vulnerability, the lack of resilience, lack of government, lack of environmental resilience in Haiti all came together to cause that disaster. It wasn't particularly a big earthquake. This was a big earthquake. A magnitude 9 earthquake generated a tsunami in excess of 40 meters in some places. I have the wrong number here for the deaths were actually a little bit less and the losses were a little bit more. But this is a picture. You can see a car upside down on a 3-story building. This was a big tsunami, make no mistake. Engineering was as good as it could have been. This house building here was actually picked up wholesale, did not fall apart during the magnitude 9 earthquake. It maintained structural integrity. how the tsunami picked it up and carried it about 30 meters and deposited it with a scratch that was less than a meter long on the road where it was deposited. You can see here, these are pillars up to about 3 meters, the foundational pillars that maintained somewhat of integrity, but as the building was floated, it just pulled the pillars straight out of the sand, of course bent them down, but basically stood no chance. The other thing the Japanese did right in this event was move the vast majority of their populations inland. The tsunami inundation zone here is outlined by red. You can see the metropolitan area of Sendai off to the left side of this, and most of the area that was inundated by the tsunami was rice paddy. You can see the port facility over here. This is a very industrial area in the north coastal part of Sendai. But from here all the way down to Fukushima is mostly rice paddy with some small villages in between. So that was a very good idea. The tsunami is actually stopped by a raised motorway through here. The motorway is raised about 3 meters high, which actually acted as a bit of a buffer dam that kept it from going another couple hundred meters inland probably. The Japanese also built a series of seawalls, about 5 to 6 meters high in places. They got completely overrun by the tsunami. They did a remarkable job. The seawalls actually had dual purposes, where they could keep out, more than dual, multi-purposes, keep out tsunamis, ideally. The last 16 tsunamis in this area were about 5 to 7 meters high. The 17th tsunami was another 10 to 15 meter high one in 869 AD. I also put this image up because I believe here in this thing there are 2 or 3 backhoes, which are 2 or 3 times more backhoes than existed in all of Haiti in 2010. Not only did the Japanese build massive seawalls, but they also used ecosystems to buffer the tsunami. There's about 300-meter thick coastal forest that got mowed over like toothpicks by this event. So they did everything they could have to prevent this engineering-wise. They bioengineered, they green engineered, rather. They also used gray engineering. They put everything at it, and it was still a massive event. And I would argue that it would be a lot more losses were it not for the engineering efforts they made. Finishing up talking about bioengineering, this is an image of Banda Aceh after the tsunami. The inundation went about 4 or 5 kilometers inland. I would argue also here, and I haven't done the real work on this yet, to figure out if this area would have been mangroves prior to habitation, prior to human habitation in this area. You can see evidence of tidal channels in this area over here, intertidal areas, and it certainly is tidal now as the sea inundated with the land subsidence in this area. I would argue that if this weren't habited by people, if it had gone back to mangroves, that the deaths would have been a lot less in this area from the tsunami. As would this guy, Sharial. He's a crab fisherman that we spent a couple of days with learning about mangroves and how he earns a living in Banda Aceh, and learned something interesting from this guy. He was laughing, and I'll tell you why he was laughing in a second, but first of all, after spending a few days with him, he turns out to be have a rock band, and they sing Achenese protest rock and roll. So Aceh was, of course, in the middle of an insurgency when the tsunami hit in 2004, which also reduced their resilience. But Sharial was laughing because these NGOs have been planting mangroves all over the place, and it turns out of 2.6 million mangrove seedlings planted, they had a 98% mortality. So an awful lot of wasted energy and a lot of wasted money in this area. And Sharial was laughing because they actually planted the wrong species in the wrong places. This is a Bruguera species, I think, or Soneratia species here. In the background, you have a Rhizophora species. So this was doomed to die. He knew it was going to die. He tried to tell them, but they said, oh, what do you know? You're just a dumb crab fisherman. And then we went further down the coast where it was out of reach of the NGOs who were planting the wrong species. We saw some pretty remarkable natural regeneration of the ecosystem when it was left alone to its own devices. In summary, this is kind of my summary punchline slide. I'm not arguing that we need to have a bunch of people out there who can do everything very poorly. What I would like to argue is that we have specialists that have disciplinary strengths. I don't want social scientists out trying to figure out the frequency and magnitude of an earthquake or tsunami in an area. I don't want to have natural scientists trying to figure out the economics of an area. It doesn't make any sense, nor do I want necessarily a policymaker building structures or any of these things mixing together. But I do think we need to have some interdisciplinary communication, respect, and understanding for these different things, so we can have some ways of communicating between the different fields here that we're dealing with. So we need to respect the disciplinary specialty. There's going to be some people who really want to go deep into disciplinary. We need those people. Make no mistake. We also need people that can work between these. What drives the system is at the very top there. Academia is responsible for constraining problems. NGOs and international organizations set development agendas. They need data. They really are kind of doing guesswork on their policies they're suggesting to countries, especially developing nations. They need to have communication with us, and we're not very good at communicating with them. Similarly, the public sector outside of government is going to be responsible for implementing solutions. They've got certain needs and agenda for growth and economic growth and planning, that sort of thing. But they need to work with NGOs also. So I'll finish with that. I was going to talk about policymakers, but I'm going to stop there. I'll go back to this slide. I'm going to stop there and leave it to questions. If there's any questions, I'd like to hear them now, or I can also talk a little bit about some investment ideas that I have about how we might be investing in the wrong things. I'll stop there and open up the floor to any questions if there's actually anybody out there.
Hi, everybody. I'd like to, Elizabeth, I encourage you to send a message via the chat, and then I can read the question to Brian. I'm curious about the next part of the talk as well, but one of the things that I was wondering about in terms of this interdisciplinary, transdisciplinary approach is whether that is realized in your post-disaster surveys, and what does a post-disaster survey really look like? What do you do, and what's the point of it, and how does that work?
Well, I'm glad you asked that, because we tried doing a really, truly interdisciplinary survey in Samoa in 2009, and it failed miserably. We ended up getting a bunch of people together. My colleague Dale Dominy Howes and I got a team of engineers and scientists and economists and fisheries experts and policymakers and just about anybody you could think of to do a survey after the tsunami there. And we ended up with a team of about 40 people. And it was really too many people. And we weren't able to keep track of everybody and actually collect the data in an efficient manner. So that was kind of, we call it burnt pancake. The first pancake you excuse me, you really flip off and give to the dog, but everyone after that hopefully will be perfect. What happened with that survey is I ended up being seconded to a group with the fisheries, the Samoa fisheries ministry, and we went out and surveyed changes in fish populations and damage to the reef. And at the end of the day, we were meant to go back to our sort of camp. We had camped out in a dorm at the local university and report our findings. But what happened is everybody was so shattered at the end of the day from being in the field, we weren't very good at completing reports, and even brief meetings were challenging. So really, there's just a little bit too much information coming from too many people all at once. So we're still learning how to do that, and that's the protocols we're still working on doing. What we need are fast and light teams of maybe 5 to 10 people tops to go in the field, who each one has a certain specialty that can work together. Whether an engineer can do, 2 engineers can actually survey an area efficiently is a different question, but that's something we're still very much working on. The word transdisciplinary is a bit of a buzzword these days, and I consider that I have kind of a rather strict definition for what I consider transdisciplinary, but part of it involves using what we call extra academic information. So the lessons from our man Sharial, the crab fisherman, he knows things that I don't. He knows things that people who have been studying mangroves for their entire careers don't. And we need to figure out ways to effectively incorporate knowledge from people like him into our studies to reduce the risk of disasters. These are the people who live with the environment every day, and they see things, they know things. In some cases, they have indigenous knowledge of past events and how the best way to react is versus, again, bureaucrats from Geneva or professors from Switzerland or from Singapore that are coming into these areas and trying to learn and use our acquired knowledge in different ways. So I think it's critical that we open up our minds to these people and actually figure out ways to incorporate them into the process.
I have a question from Melissa. I think it's from Melissa. Given the disaster element of natural events, when we think about resilience, what integrated solutions do you think would have important implications for reducing negative risk?
Read it one more time, and I think I got it.
Given the disaster element of natural events, when we think about resilience, what integrated solutions do you think are the best?
I think what's really critical, and this is kind of ironic, but one thing that I see happening are battles between economic interests and what's perceived safety. So after the tsunami in 2004, the Sri Lankan government decided to put setbacks into coastal setbacks into play. And this is an area where they don't really get hit by typhoons, Indian Ocean typhoons. The last tsunami there would have been probably this 1350 event, so 700-800 years ago. What that does is, without having a conversation between the planners, in this case, and the geoscientists, they think they're doing what they think is best by moving people out of harm's way. But frankly, what they're doing is moving people away from their economic engines. So if you have people in the Indian Ocean basin, we learned are actually more reliant on natural resources, and they're mostly poor people who live in the coastal zone there, whereas in the Pacific basin, it's mostly very wealthy people. By moving them away from the coastal zone actually makes them more vulnerable to disease, to poverty, to hunger, than actually leaving them there close to their livelihoods when they're really, really not likely to get hit by another event because they haven't had that conversation about frequency and magnitude of events. In the case of things like climate change, is we could be looking at, if not more frequent, more powerful tropical cyclones. That might be an area for a time for considering moving assets out of harm's way. But if you think about something like Hurricane Sandy, and I think we've talked about this in the SAGE group, I think a really interesting study would be to think about how much income has been generated in the coastal zone between events compared to the acute losses from a given event. Now, that's a very cynical almost way of looking at things if you're only considering economic losses, because there's also human losses. The thing we've got to get down, and there's no excuse for us not getting this down, is proper evacuation from tropical cyclones. There's no reason that in our society we've got the best cyclone prediction models in the world that we can't get people out of harm's way when these disasters hit. But also in a country like America, where we've got freedom, we can't force people to move. In other countries where governments are not so willing to let their people die, they might have different reactions. So I think it's a very complex thing, but I think we really need to understand this relationship between economic generation of income in these hazardous areas versus the recurrence interval of the earthquakes. I think that's a very complex field. There's a lot of work to be done there.
Yeah, that's really interesting. In a related question, Sydney Clouston comments that prevention is important and building on lower elevations really is a significant problem. When you've gone out to look at this, do you see that it's economic or policy-driven approaches to both cause it and ways to address the landslide-prone building?
Landslide-prone. Are you talking about landslides?
Oh, sorry, no. She was just commenting on building in lower elevations.
Yeah. So I go back to that slide, which really struck me when we made it up of why would you put anything, a house, a building, a factory, a business in an area where there's hazards that exist, because you can generate income from it. So why do factories put themselves in the floodplain in Thailand, or why would a very wealthy person build their house on the Outer Banks of North Carolina? Well, I think that's just foolish, but not generating much income from that. But why would you put an amusement park on Coney Island or something? Because you can generate income from this, or the boardwalk in Santa Cruz, or anything. Why would you put Port-au-Prince City right there? Why would all these people flock to an area where it's right on these faults? Because you can generate income there. So I think people look at the opportunity to generate income in these areas, and they'll say, okay, think about my degree of risk tolerance, and then make the decision to actually live there. And I think they're saying, okay, yeah, I think I'm going to generate enough money, even if there's a disaster that hits. I will have generated more income than I'll have lost. The government will bail me out. Insurance will bail me out if it's that. I really hope I don't die. There's always good things. That's why we also like to separate out mortality and economic losses. I could talk a little bit about that, but I know we're running short on time. So if anybody's curious about that, I'll leave this graph up as food for thought. We can talk a little bit about that if you like.
Well, now you've got us interested.
Okay, so we were looking at that example. So if you think about this image of the hinterland in Haiti, if you have a magnitude 7.1, 8.5 earthquake, these people are going to live because their house is going to fall down and may or may not fall down. But if it does fall on, it's going to piss them off something fierce, and they're going to have to dust some palm fronds off their head and drag their rattan mattress out from the house. But they're most likely not going to die. If they went to Port-au-Prince to actually seek a little bit better economic opportunity, essentially their income is going up in this case. Your income goes up, but in this case, your losses, your mortality can actually go up here because you've got just enough money to build a really dangerous house. But then as your income continues to increase, your mortality goes down as you can build better and better houses. What we find, however, is that as your wealth goes up, your losses increase. So you have, in rich countries, you tend to have very high economic losses and much lower mortality for similar events. Whereas in poor countries, you tend to have very high mortality and low economic losses. They simply don't have the money. But there's some sweet spot or horror spot really, where you've got just enough money to make things dangerous. You can actually really increase your money, increase your mortality rather, and your economic losses are still relatively high. So we did some modeling or some data collection on this to show we actually started separating out hazards and seeing if hazards cause different levels of economic loss. But that's another 10 or 15 minutes. I won't go into that.
Okay, I do have more questions, but I know it's now 12 o'clock or 1 in the morning. And so I should probably thank you very much and thank our participants. I found that really fascinating, and I learned quite a bit in the, as I hope the integration of social and physical science is really what makes this particularly exciting. So thank you, Brian. If you can hold on just 1 minute, but we can, I'm getting other notes from people saying thank you, great talk. So I think it was really good.
Well, thank you, Elizabeth. Also, please, if you have any questions, feel free to follow up with an email. You can find me on the Yale-NUS website or on the SAGE. I'm sure that on the SAGE website, our contact information is there somewhere.
Yeah, we'll be sure.
And thanks a lot for having me. This has been fun getting to talk together. It's the first research I'm thinking I've done in a while, so it's nice being away from the administration.
All right. So a question that I have, and I'm sure people will get off, but when I was looking at your graph on mortality and income, shouldn't that be really percent of GDP? Because that's the amount that it hurts, is not the dollars, but the percent, right? So in Jamaica, when they have when they have a loss, it might not be many dollars, but it could be a significant percent of their GDP. Okay,
so I'll show you the data then. This is the model we had where we're looking at if you have mortality on this axis and economic loss on this axis, the size of the bubble is related to income, basically GDP of a nation. So small is poor nations, bigger dots are big nations. So we figured this is what it should look like. We actually plot out data from different hazards. This is what it does look like in the real world. This is all disasters from, I believe, 1980 to 2010. We had to clean up the data a lot, about 3,000 data points here. You can see that there's a clustering of wealthy countries down here. We've got large economic loss and lower mortality, and there's more of these smaller dots up here where you've got higher mortality and less economic losses. It's a bit messy, but the real interesting thing from this are these events up here. We've got very high mortality in wealthy countries, and they're from heat waves.
Yeah, heat waves. Right.
it takes you a while for you to get your brain around that graph. There's a lot of information in it. And it's kind of, as my student said, it looks like, he called it psychedelic effervescence.
Yeah. And so are there small dots underneath the big dots?
Yes.
Yeah.
So I'll show you the next graph, which, yeah. So my students, I'm very proud of my students for doing this, and I'll let you wrap your brains around this one also. I showed them that graph, and I said, I don't think people can get that because there's just too much going on. So they came up with this way of presenting it, where they actually combined all the losses into one point for middle income, low income, and high income nations. So for instance, all the deaths from heat waves here, there's 100,000-ish deaths in the time period in wealthy countries from heat waves. And the thing that this graph shows, which is really interesting, is I'm working on getting this published right now. So there's actually more deaths, because this is a log-log scale, there's more deaths from heat waves in wealthy countries than every other disaster combined. Mm. So if you combine the deaths from earthquakes, floods, tropical cyclones, which are the big ones there's still more deaths from heat waves in wealthy countries than any of those other disasters. And I bet money that wealthy countries are investing far more in earthquake, flood, and tropical cyclone measures than they are in heat waves.
Absolutely.
And they also cost more, which you can see on the graph also. So there's more economic loss for us. That's their priority.
I wonder if you looked at, and this wouldn't be, it's a certain extension of research, but if you looked at like Australia, where this would be maybe the most extreme?
It's interesting that most of these events here are from a couple events in Northern Europe in 2003 and 2010, I believe. Yeah. Wildfires are also a bit more extreme in wealthy countries than they are in poor countries, and that's mostly due to Australian wildfires and economic losses associated with wildfires in Australia and the U.S.
I think one of the things that for me is great about this is it argues for why climate change is relevant inland as well.
Yes.
Those heat waves affect primarily inland, low-income, highly impermeable areas.
You're absolutely right. And they hit low-income people in high-income nations, vulnerable people in high-income nations, so old people, mostly old people, in this case, who are not very mobile. You're absolutely right.
Yeah.
And the solution to this it argues for more grassroots solutions rather than top-down solutions. So some of the research done on this says we got to get more local networks in place looking after people, because there's nothing that a large central government can do to get to those impermeable areas where there's lots of highly vulnerable people.
Yeah, yeah. Well, we can plant a lot more trees.
Yeah, that would certainly help.
And as it turns out, I'm sorry, I could talk about this a long time. You probably have to go, but as it turns out for heat waves, and you probably found this in your research, my understanding is it's actually what happens overnight that's the most important.
Exactly.
If people don't get a chance to cool their bodies down overnight, that's when they die.
That's what happened in France in 2003, I believe. There's some crazy, something about the omega blocking pattern or something in the North Atlantic prevented whatever the radiative cooling, set up some kind of a bizarre high pressure system, I guess, that prevented that radiative cooling that usually happens at night from happening. There's some inversion layer that kicked in and just clamped everything down. It just didn't cool off overnight.
Yeah. Yeah. Well, I think you should publish that. That's going to be a good article.
Well, I'm proud to say it's been rejected from the best journal in the field already, so I have to find another journal to put it in. But
well, the good news now is you can get cited from a lot of different things.
Yeah, well, we'll just get it published first.
Oh, good. Well, I thought that was a great talk. I got a little as a non-soils person. It took me a while to put together, just so you know, why progradation. matters for tsunami and how it connects to upstream lack of cover.
Yeah,
so,
the idea is that, I mean, the strange thing, I can go back a few slides here, but the strange thing is we looked at these rivers in Haiti, and they just even to anybody who's looked at landscapes, just didn't look right, because the rivers were kind of like just full of sediment. You just don't see that in the tropics so much, because the kind of erosion that happens is different. So if you see these bright stripes of rivers coming down here, you don't see that. That's just unusual. So you have a lot of sediment coming down here. We shake that sediment loose, so the sediment comes down the rivers, it keeps getting pushed out by the strong currents in the rivers during the rainy season. When it gets to the coastal zone, it just stops and gets deposited right there, because you lose the force of the flow that's pushing it down the river. So it all gets deposited right there in the coastal zone at these deltas in this case. And when it happens there, you end up with a lot of sediment that piles up there quickly. And then when it gets shaking, it shakes loose, and it can actually displace water that then generates a tsunami.
Okay. So really, the lack of soil cover, the lack of planting,
yes,
upstream causes tsunamis.
That's exactly the jump we're trying to make here. Yes. In this case.
That's fascinating.
And the key is that deforestation is caused not just by poverty, but by a long history of colonial, post-colonial reparations, dictators. Everything lines up here in this really complex mix-up, or melange of craziness that makes this place this complex system. So to understand it just by looking at one thing is kind of ludicrous.
Yeah. So then it also would argue for why the UN red is really has some potential.
It's especially right here in this region where we've got so much deforestation happening, not only because of right here in Southeast Asia because of palm oil, which we're going to be starting to look at with a group from Pomona College in January, but also in places like Nepal, where you've got it's interesting. You've got more people from Nepal going to the Middle East for work, and they're sending remittances back to the poor villages. And people are taking those remittances and improving their land. So they're either taking down more trees to plant more land, or they're actually building roads to these rural villages. But kind of like the case of Port-au-Prince, they're able to build roads, which is good, but the roads are built like crap. So when the rainy season happens, the monsoon season happens, you get a lot of landslides that are generated because of the roads. So that's another project we're working on right now.
Cool. Very interesting.
Well, thank you. It's a lot of work to do. So any of this stuff appeals to you or anybody else that's still there and want to work on a project, give me a call. Got lots of work.
Good. Yeah, I think this would be a great talk for the resistance. I think to talk about the idea that I floated about you coming to UMass. Is anybody else still on the line? I don't want to bore people, but yeah. I think this would be a great talk, trying to really explore these interconnections in how disaster is created. Exactly what you're doing. Yeah, I think it'd be good. I think we could. It's
really kind of an ADHD approach to this stuff. I wish I had a fleet of graduate students to take each one of these and explore it and really start knuckling down this stuff. But hopefully, if I keep, thank you, Anna. If I keep, clocking away at it and keep getting people's attention, maybe people can start with it and run with some of these ideas. I'm not greedy with this stuff at all. So anybody wants it, give me a call and take it and run.
All right. Well, we should probably let you get to bed.
I think I'll take you up on that.
Thank you very much for doing this, Brian. This was really fun.
It's been my pleasure, and thanks everybody if anybody's still there, and thanks for giving me the platform.
Okay.
All
Bye.
right. Take care.